Hi everyone, I'm going to be doing problem 2 from homework 2 this time. I'm doing this one because it was probably the hardest problem on the homework for me, so I figured maybe talking about it and getting like input into my answers might be helpful to better understand the concept. So the problem starts where we have these three rigid bars. We have a mass m1 that's constrained to move up and down, and we have a mass m2 that can kind of move in a circular motion, around the pivot point. And the whole system is changing with respect to theta, so that's our general coordinate. We can define the whole system with respect to that. So first of all, we need our position vectors. What's it called? R1, mass 1 is actually pretty easy. That's just moving in the easy direction. And in terms of theta, that's just a little like theta L cosine because we want this vertical component over here. And you multiply it by 2 because L cosine only defines one half up to M2, and then you need to get the other half. And then for R2, we could define this just by straight up doing L in the ER direction. I did also go ahead and write it down in the L sine theta direction. So I defined some EX coordinate over here, and then I said it was L sine theta EX plus L cosine theta EZ. I did that because I thought maybe later when I was actually putting all these into the same EF equal MA equation with the Allenbert's principle that it would be kind of easier, so I wouldn't have to do the frame conversions there. But maybe it might have been better to keep it in LER because then the integration would have been easier. So, I don't know. I think that's how someone else who did the other approach, and I think there's pros and cons to both. Then we have to find the velocity and acceleration. So I go ahead and integrate it once. This is a pretty standard chain rule. 2L sine theta, theta dot because of the chain rule. The negative shows up because you're going from cosine to sine. And you're doing the same for these other terms. Then you're going to go ahead and integrate it again, which is going to give you even more terms. You can pull out the 2L to the front, which is kind of nice, but you still have to do like this sine, cosine theta, theta dot, but then now there's a theta dot, so there's an extra chain rule, and you get an extra theta double dot here, and you actually do that, a bunch more times. So that's, just what's going on here. Then for the virtual displacement, by definition of the virtual displacement, we know it's just going to be the r vector that we're looking at, the partial of that with respect to our generalized coordinates times the virtual change in that coordinate. So for D1, that's just going to look like taking the derivative of cosine, which is going to be, again, that negative sign. Then for our second vector, I'm keeping it in the EZ direction here, and just taking the derivative with respect to theta for both of those. Then our forces for this problem were luckily pretty easy. Even though there's tension forces in the rod, one benefit is we're only looking at applied forces, so we're able to just look at the mass of both of the particles and put that in the easy direction, and those are our applied forces. Then to actually solve the problem, we end up, using D'Alembert's principle. I sure hope I'm saying that right. I guess I'm not. I'm not sure. There's only one generalized coordinate in this problem, which does make it a little nicer because then we're only going to have this gamma I1 term, and gamma 1I. I think velocity coefficients in this case is either the velocity vector. What's it called, derived with respect to the generalized coordinate velocity, or you can also do the position vector with respect to the position coordinate. So I go ahead and do that for both R1 and R2, and that's going to give us, I think we've seen these same derivatives like many times now, but that's just going to give us both of our gammas. Then for both parts, because this is a sum for what's for both our first particle and our second particle, in this case, M1 and M2. So we end up with these two equations where we're doing the force applied minus this MA term times the gamma. And then go ahead and work that all out, I think because of how I had it in separate directions, it was a little easier to do this step because then the hardest part was just keeping track of having so many terms. But I was able to get through it, and then I combined everything, brought over. I ended up dividing by negative L to cancel out the negative sign, and also there's just kind of an extra L term that wasn't really needed there. So we end up with this equation of motion. Then for the natural frequency, I went ahead and applied some of the tips that were given in the problem. So for example, we know that sine of theta is essentially theta. we know that cosine of theta is going to be 1. Sine squared of theta is basically 0, as well as like theta dot squared, theta dot. These are all kind of basically negligible. So what we end up doing is canceling this out because of sine squared theta, cancel this whole thing out because of theta dot, and then we're just left with this equation divided over to get the omega squared term, and then we can take the square root of that and divide it by 2 pi to actually get the frequency of the oscillations in hertz. So that's kind of my approach to the whole problem. Like I said, it was the most difficult problem I think on the homework. But now looking back on it, I think that I feel more confident about applying the the Allenbert's principles. It's just kind of a lot of terms to keep track of. Thank you, and let me know if you have any questions.